All right, what were we doing? We needed to work on this integral a little bit more. EP, it was EA over R, e to the j omega t minus kr. And we needed to combine those terms that were out front. It was 1 over, what was in front of each one? Yeah, 1 over jkx over r. So the big r's at the bottom go to the top, so you get big R squared when you combine them. And then you actually get a j squared. We don't want to turn that into -1 yet. K squared, and we had big X, and we had big Y. That's combining those terms at the front after we evaluated the integral. And then in here, we had 1 along the X, e to the j, and then, let's see, there was a half in there. It was kxx over r. Oh, but after we evaluated it, right, it was k big X a over 2r minus e to the minus j k big X a over 2r. And then the other one was e to the j k big Y b over 2r minus e to the minus j k big Y b over 2r. That's where we were. Combine those. Now we will make our substitution again. We want to come up with new variables that we can use that hold all the diffraction information, and we'll put this nasty thing in a better form. And it's very similar to the single slit. Alpha is 1/2 K A sine theta. Oh wait, no, I'm sorry. We don't use sine theta now. Now we're using big X over R. All right. And then beta is 1/2 KB big Y over R. So we dispense with the thetas on this one. We just went to big X and big Y. And let's see. So if we make those substitutions, what are we going to get here? We're going to get that we have E A over R, e to the j omega t minus k big R. And what kind of a mess are we making here? So remember, we had to use these substitutions here. It looks like they're going to be in the bottom, right? Because we have Ka, let's see, so we're going to have, let's see, we have K big X and R on the other side. So we're going to need to bring in 2 2's to make that substitution. We have K, big X, and R taken care of. So let's go ahead and just write them down there, alpha, beta. But we are going to need to deal with this A down here that's in alpha and beta, so we need an A and a B up there to make to account for that. So I think that took care of everything except the J's. J squared. Okay. Yeah, that how's that? Okay, so that turned that into that, and then e to the j stays j, and then we have 1/2 kxa over r. 1/2 kxa over r. So there's just alpha. E to the j alpha minus e. This is of course what we wanted to happen. E to the minus j alpha, and guess what? E to the j beta minus e to the minus j beta. And just like the single slit, these will turn into sines, right? And that will turn into basically the area. So let's see, are we ready to write this in a nice form yet? Let's see, this is going to turn into EA AB over 4R e to the j omega t minus kr. All right, so that came over there. And then what was that sine formula? It was, let's see, there was a 2 in there. We're missing a 2 here, so you need 2 2's. So those are going to take care of that 4. But that'll be a 4. And then we have this with the j. It was 1 over 2. J will turn into sine alpha, sine beta. over, and here we have alpha and beta. All right. Let's see. So when that 4 cancels that 4, we're going to end up with the nice version of this thing, which is the E at P, E, A times the area of the slit over R, E to the J omega T minus KR, and then sinc alpha, sinc beta. Okay? Sine alpha over alpha, sine beta over beta. So just like the slit, this is sort of your incident field. This is the wave part, and this is the diffraction pattern. And finally, if we wanted to write it in terms of irradiance, we'd get that it's the irradiance that would get there without the slit times sinc squared alpha, sinc squared beta. So basically, the result we get for the square aperture, or the rectangular aperture under these approximations, is that it diffracts like a slit in one dimension and it diffracts like a slit in the other dimension. It's sort of just the product of those two diffraction patterns. So I've got a small slit, so here I'll just show you a still image. It's very hard to see these live because the central peak is so much stronger than all the cross peaks. So here's a little bit of a manipulated image of what that pattern looks like. And you can see, since it's rectangular, the spacing on one dimension is different from the spacing in the other dimension. So that's why it looks like that. It's very hard to see the peaks off in the corner because the differences in irradiance between the different lobes is very different. But that's the basic idea. And one thing I want to point out about this is this diffraction integral that we developed isn't really limited to a square or a rectangle. We did this in a Cartesian grid. So by sort of doing the integral, and you could add up different integrals, you could do sort of any shape you want, really. Now, certain specific shapes, like a circle, you would want to do with polar coordinates. You set up the integral in polar coordinates, and the answer involves Bessel functions, and we're not going to do it. Okay? But this is the basic idea of how you get diffraction from an aperture.